Now that we've defined the dot product of two vectors as the product of their parallel parts, we can use that construct to add up the cumulative effects of a force acting on an object over a distance along a path. So suppose an object moves along some path through space like that, and in this direction, and we pick out some particular moment along that path, say this moment, and at that moment we draw in the instantaneous infinitesimal displacement vector, which is like a little step forward in your current direction. So a small vector tangent to the path, an infinitesimal vector, and let's show also the instantaneous force acting on that object. So we can see that we are turning to the left, so there must be a force that's at least partially pointing to the left, so we get an acceleration partially to the left relative to the velocity. The velocity, of course, would be in the same direction as the displacement tangent to the path. Okay, so there's our force and displacement at that one instant as we're moving along this path here. So I want to express the dot product F dot dr, the product of their parallel parts, because that will tell us the extent to which the object is speeding up, slowing down, and or turning. So our force, written in terms of components, will be Fx I hat plus Fy j hat plus Fz k hat. And our displacement vector, dr, in terms of components, dr could involve a small step in the x direction, a dx, times I hat, pointing in the x direction, plus a small step in the y direction, dy times j hat, plus potentially a small step in the z direction, dz k hat. And having done so, we can write our dot product. F dot dr, remember that dot is like a fat dot for a multiplication, specifically for this method of combining two vectors to make a scalar. And we have two definitions for it. The original definition for a dot product of two vectors would be the product of the magnitudes of the two vectors times the cosine of the angle between them. That would be theta there, the angle between them. And our second equivalent definition for the dot product would be the sum of the products of their components. So Fx times dx plus Fy times dy plus Fz, the z component of the force, times dz, the small step in the z direction. Okay, so that's the dot product at this one instant, and we want to find the net effect, the cumulative effect of a force acting over a distance as the object moves all the way along this path. Assuming that the force continues to act on the object all the way along the path. So the force could be varying along the course of the path. We want to find its cumulative effect. We want to add up all of the F dot dr terms at every point along the path. F dot dr here plus 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 F dot dr here at every point along the path, adding those up. And so if we're adding up what will require an infinite number of infinitely small terms, then we're integrating. So this integral we call the work done by the force. Here's what we mean by the work done by the force. This integral, this sum of F dot dr at every point along that path. So capital W for work. We're going to take F dotted with dr. That's a very small value there because dr is infinitesimally small, but we're going to add up an infinite number of those infinitely small things. Now for the limits, the upper and lower limits on this integral, since this is what we call a path integral, let's see here, this is a path integral, moving along the path. Instead of just putting a simple upper and lower limit, I'm just going to write down at the bottom of the integral symbol the word path. Meaning we're going to compute this product at every point along that path as we move all the way along that path. So that'll suffice for our limits. This is sort of where we say where we are going to be doing this summing. And okay, this dot product produces a scalar. So our work itself here is a scalar, just a single number, not a vector. It's the scalar product of these two vectors. And we've got a couple other ways that we can write that. So f dot dr could be expressed as this here, fx dx plus fy dy plus fz dz. Let's do that. I'm going to replace f dot dr with fx dx plus fy dy plus fz dz. And then, since the integral of a sum is equal to the sum of the integrals, I could break up this one integral along the path into the sum of three separate integrals. An integral of fx dx along the path plus an integral of fy times dy along the path plus an integral of fz dz along the path. And there, let's bracket this as our definition of the work done by that force pushing an object along that path. Incidentally, we can note here the units for work. Since we've got force times distance, then our units here must be newtons times meters. Force in newtons times distance in meters. So the SI unit for work, Newton meters. Newton meters, and that's how we say it. Newton meters meaning a Newton times a meter. Okay, let's apply this to a number of different scenarios and instances. There are different ways we can see this coming into play. So our first example here, this one-dimensional example. For a block moving along the x-axis. Okay, a block moves along the x-axis, passing through the origin at time 0 with some positive x velocity, and continuing to move in the x direction the whole time. That's important. Moving in the positive x direction the whole time. So it never turns around. That makes our path particularly simple. We don't have to worry about reversals on the path. We're moving just in the x direction the whole time. From x equals 0 to 1 meter, no force acts on the block. Okay, so I'm going to start graphing our force as a function of position here. So from 0 to 1 meter, no force acting on the block. So as the block moves from here to here, there's no force on it. Then from 1 to 3 meters, a force of 2 newtons acts on the block. So a constant force of 2 newtons acting on the block as the block goes from 1 meter to 3 meters. Then from 3 to 4 meters, a force that starts at negative 2 newtons and decreases in magnitude linearly with distance. Decreases in magnitude linearly with distance to 0 newtons. Okay, so we start at negative 2 newtons and decrease linearly to 0 newtons as we go from x equals 3 meters to 4 meters. Okay, and then from 4 meters on, no force acts on the block. Sketch that graph for the force versus position. We've done that and determine the work done on the block by the force as the object moves from x equals 0 meters to x equals 5 meters. Okay, the work done, capital W for work, will be f dot dr along that path. Okay, looking at our definition here, f dot dr along that path can be broken up into these three separate integrals if we're moving in 3D, but our force has no y component and no z component. Those are both 0, so both of those integrals would vanish, and we would just be left with the integral of fx dx along the path. Furthermore, since the object goes in the x direction the whole time and never turns around, there's no reversals, that makes our limits easy to write. We can say fx dx, and then for our lower limit, we can say it starts at 0 meters and went directly to x equals 5 meters without changing direction or reversing or anything. So we can even put in our upper and lower limits. And we know that on this graph that represents the area under our curve, or between the curve and the 0 axis, from 0 to 5 meters here. So let's get that area here. That looks like 2 newtons times 2 meters there. And then half of negative 2 newtons times 1 meter there. So our area is the area of the rectangle, 2 newtons times 2 meters. And then minus, since this area here represents negative work being done, minus half of 2 newtons times 1 meter. So that looks like 4 minus 1, or 3 Newton meters of work altogether. 3 Newton meters of work done by that force on this object as it moves from 0 to 5. Note that when the force was positive and the object was moving in the positive direction, when force and displacement were both pointing in the positive direction, that was this rectangular area here, we've got positive work being done. That force is speeding up the object when those two vectors are aligned. But down here, this negative triangle, that's when our force is pointing in the negative x direction, but our displacement is still in the positive x direction. We're still moving to the right, but the force is pushing back to the left. So we're doing negative work, slowing the object down during this part. So this area represents a tendency to speed up since our work is positive, and this area represents a tendency to slow the object down, the work being negative. And here's our net result over here. Overall, we had a net positive work. Okay, next example. A block attached to a spring on a frictionless horizontal surface, subject to a restoring force, a key term, a restoring force given by this formula here. So this time, instead of being given a force versus position graph, we're given a force versus position function. K is the constant, the spring constant, and we're given a value for K, 24 newtons per meter. Note, this is newtons per meter with divide there as opposed to newtons times meters, the unit for work. Find the work done on the block by the force as the block moves from a position of x equals plus 0.5 meters to minus 0.5 meters, meaning from 0.5 meters to the right of the equilibrium point to negative 0.5 meters, or 0.5 meters to the left of the equilibrium point. So it's starting here and moving to the left. It's going to swing through equilibrium and continue on to this position. Okay, we want to find the work done by that spring force over that interval. So write down our definition for work. F dot dr along the path. And again, we're only moving in 1D here, so there are no y components or z components to the force. So those two integrals vanish. We'll have just this integral to do. And since we're only moving in one direction the whole time, only moving to the left, there are no reversals, no turnarounds. That makes it easy to state the limits of our integral. We're going to go from x equals 0.5 meters at the beginning to x equals negative 0.5 meters at the end. So we've got our upper and lower limits of integration. Now, since this time we're given the force as a function of position, fx as a function of x, we can substitute that into our integrand. So this becomes the integral of the opposite of kx dx from 0.5 to negative 0.5 meters. Okay, we can find our antiderivative of the opposite of kx with respect to x. That'll be the opposite of 1/2 kx squared. Put that in brackets. I'm going to evaluate that at the limits. X equals negative 0.5 meters and x equals positive 0.5 meters. Okay, continuing to evaluate that integral. Plug in negative 0.5 meters for x, and we'll get negative 1/2 times k times negative 0.5 meters squared minus this same thing evaluated with x equals 0.5. So minus negative 1/2. So this is the antiderivative evaluated at negative 0.5 minus the same antiderivative evaluated at x equals 0.5 meters. There we go. And what we notice here is that we've got equal terms. That negative disappears when we square. So we've got negative 1/2 k times 0.5 squared minus negative 1/2 k times 0.5 squared. They sum to 0. 0 net work was done. By this force, by the spring. Why? Why was 0 work done in this case? Let's examine. Consider as the block moved from this position towards equilibrium. As it's moving towards equilibrium, the force on it, the spring force, would be to the left. The stretched spring pulling the block to the left, and the block's displacement during that time was to the left. This little example displacement vector, dr. But then, after the block passed the equilibrium point, the force on it reverses direction. It's a restoring force, so it always pushes back towards equilibrium. So, past the equilibrium point, our force reversed direction. As the spring was compressed, now the force is pushing the block to the right. As the block continues to move to the left from 0 to negative 0.5 meters. So there we clearly see by drawing the vectors that during half of the trip, force and displacement were in the same direction. So they're reinforcing each other, supporting one another. That force is doing positive work. This was our positive work being done during that first half. And then in the second half, force and displacement are opposing each other. So this force is having the effect of slowing the block down, doing negative work, since it's 180 degrees apart from our displacement vector. So the positive work done during the first half was canceled out by the negative work done during the second half. So did the spring do work during the journey? Yes, positive work at first, then negative work. The net work done was 0. Note also that the block started at rest and then ended at rest. That's related to the net work that was done being 0. We'll be coming back to that point.